Last week we covered Ethereum at a high level and how it's different from Bitcoin. And then we started to talk about cryptographic foundations, which are then necessary to build a blockchain. And we talked about wallets. Are there any questions on any of those topics? Well, let me ask questions. So what is the big difference between Bitcoin and Ethereum? Yeah, smart contracts were the big innovation. And then we talked about cryptographic foundations, talked about the difference between symmetric encryption and asymmetric encryption. Anybody want to explain that briefly?
Symmetric one, we will have the same secret code.
Right.
And we'll both use the same one to encrypt it. If there was let's say, a public key and a private key, so let's say it would be my email address and my password. When you were going to send me an email, you will be encrypting it with the public key. And then once I receive it, I have to first verify your signature and then decrypt it using the secret key.
Okay. And how do I generate a signature?
I can.
Sure.
I think a signature is a hash of a message that is being signed, and that is like the message itself plus the secret key.
Okay, and signed with what? Okay, yeah, perfect. Thank you. And then we talked about wallets, that the term wallets is a little bit of a misnomer. Does anybody want to explain what a wallet is? That's right. So you take it manages the private keys of a user, and you use these private keys to sign transactions that are then being submitted to the blockchain. Great. And then here, right, with the Enigma machine. Okay, so we talked about public, well, we talked about symmetric encryption and asymmetric encryption. And now we're getting into hashing, which is also an important cryptographic technique that is extensively used in blockchain. And so hashing is used for storing verifiable pieces of data descriptors. They're very easy to compute, but hard, if not impossible, to reverse. So you have h of x will be, so x will be hashed into x prime, and the reverse cannot happen. So you cannot go from x prime to x. Go ahead, Mark. Oh, yeah, of course. Thanks. And the other property is that it ought to avoid collision. So if you have two different inputs, x1 and x2, they should not result into the same hash. Another property that is not mentioned here is that x prime, so the hash, should be completely random, right? It should not be you shouldn't be able to influence what the hash is based on the input. And that becomes important if you think about proof of work, where the miners have to generate a hash with leading zeros, right? If they were able to influence that based on the input that they send, then they could, be potentially more efficient, but it is completely random. There is commonly used hash functions, so MD5, SHA-1, SHA-256, and Ketchik. MD5 and SHA-1 are now considered vulnerable in that you are able to generate a particular hash based on input. So they're no longer considered secure, but they're still used at times. Not in blockchain technology. I'm more referring to, older Web 2 technology. I use hashing extensively at Microsoft to basically create identifiers for malware files. And then if you think about, so let's assume, Microsoft has a set of malware files, and they can hash them all. And then on the client, if any file comes in and gets saved to disk, the client can say, create a hash, and then basically check that against the database of known malware, right? And if there's a match, then you know that the file that's on the endpoint is malware. Did that make sense? It's basically a lookup that you can perform without actually having the content of the file. And then another question, what could you do if you create hash collisions? But let me actually differentiate a little bit. If the input is the same, then it will always generate the same hash. What I am asking, what if you're able to generate the same hash on different inputs? So you have h of x is x prime. Now, what if you're able to create something like a different piece of content that hashes to the same value? That is more what I mean by hash collision. What you mentioned is if the kind of the same input, right, then it would generate the same hash by design. And then the one I am thinking about the malware example that I've given you, right? So Microsoft has a database of malware hashes that are then shipped to the client, and the client checks a file. You could generate a false positive, right? Like you could take, let's say, a benign program that hashes to a malware file, and then every client that has that benign program, let's assume like a popular program like Notepad, would think it's malware. A little bit contrived, but I'm not saying that happened, but it is certainly possible if you use a weak hash like MD5 or SHA-1. And any thoughts of what you could do if you reverse a hash to the original value? So you have a file and I have a file, and we want to check whether we have the same file, right? We could exchange hashes, and theoretically we're not exchanging the files. But if you're able to reverse it from the hash, then the confidentiality and the privacy associated would potentially be broken. Hashes are also extensively used for password storage, right? Like when you sign up on a website and you submit your username and password, the receiving end is not storing your password. It is storing the hash of the password, such that when the database gets compromised, they're not able to get all the passwords. And so what happens when you authenticate, you on the website, right, your password that you enter into the password field gets hashed, and that gets sent and compared to what they have in the database. And if it matches, then you provided the correct password. But there's a problem in that if you can pre-compute essentially tables of hash values, which facilitate the reverse, right? So you could take all like English words and maybe even do random words, right? And spend a lot of time to generate these lookup tables with the value and the hash. And then if you have the hash, you can easily reverse it, right? So the property of, okay, you can only go from value to hash doesn't hold if you're able to compute the hashes for all possible values. Because then you could just pre-compute it and do a lookup. And these are called rainbow tables, and they're readily available on the internet. Great. So this is the case here, right? Rainbow tables exist. So how would a company store a password securely? I just mentioned, hey, you could hash so they hash the password, and that's what's stored in the database. That's obviously better than clear text. But if you have rainbow tables, then you could just look up the password in the rainbow table based on the hash. Any thoughts on how you could secure it? Oh, you mean like kind of recursively take the hash and then do it again and then do it again? Well, if you think about that, if you have the rainbow table, so here there's 20 values in it. To then hash it again and hash it again is not really that expensive. So I think kind of like double hashing or triple hashing, you could generate the rainbow tables as well. Yes, sir.
So the bit sizes for the primes that are chosen for any of these algorithms is predetermined by the algorithm itself. So RSA, for example, requires whatever the bit size used for the key size, it requires half of that twice for each prime, which actually significantly reduces your range in the primes that you use because you have a maximum upper bound. The best values are going to be stacked at the upper bound. So if you're trying to brute force it, you would start from the top or maybe the top middle, either work in random directions or something, but like you kind of know where to look for what primes used for. Same goes for the other algorithms too.
So I think if your bit length is too short, and that's the case with MD5 and SHA-1, totally. But if the bit lengths are big, the number space is so huge, I don't think you know where to look. But I think that's when the bit ranges are very narrow, then yes, I agree with that. But that's why kind of MD5 and SHA-1 are no longer considered secure, because the computational power to kind of guess these values is possible, but on the other ones, at least today, not. But we learn about quantum safety, and that's maybe where things come in. Okay, any other thoughts on how to secure password storage? Very good, Duke. That's exactly right. So the way you do it is you salt the input, and then you have a salted hash. So instead of hashing the password, you concatenate the password with a random string, and then hash that. And the salt is not necessarily known. So it makes the hash values longer, making brute force approaches less feasible. Have access to a compromised data of salted passwords. How would you break it? Hashes, and you can look at like a popular password, and then you're trying to essentially break the salt, right? And you're trying to find the salt that was combined with a popular password. And then you can basically apply the salt to a rainbow table and hash that, and then match it against the database value. But that only works if the salt is small and if the salt is the same across the entire database. Ideally, the salt should be randomized for every entry. So there have certainly been a lot of database breaches, and some of them didn't hash, some of them used a kind of vulnerable hash or not secure hash, some of them didn't salt correctly, and so there's a several things that you need to do in order to store that data securely.
How risky is it? Like when a database is compromised like this?
Oh, I mean, if it is salted in a proper way, no big deal. But if it is hashed like this, then basically the attacker is able to get the clear password for, I don't know, 90% of the users, right? And it would be very cheap because all you have to do is a database join based on the hash value, right? You have two tables. The rainbow table, and then username and hashed password. And you just join on the hashed password, and then you have username and clear text password. And I think the biggest danger here is that users tend to reuse their password. So if you, I don't know, Seattle, right? You have some systems, you have your username and password. If that gets compromised, then anywhere where you use the same username password combination is essentially compromised as well. Well, like you end up. Okay, no worries.
Actually, I think big companies okay are password data that's that be compromised. Would they say that like that the salted passwords have been found out, or is it just mean like, oh, hey, someone might have left like encryption values that it could be a problem, but might not generally use it, or how?
Yeah, I mean, I think basically what they're just saying is somebody stole the username and encrypted or salt hashed password. Does not mean that the attacker has access to the clear text password. And if it's properly salted, that's going to be nearly impossible. But at the same time, if they breach the database, there's also a whole bunch of other metadata, right? Now they have their username. Maybe they have your address and phone number. Maybe they have your social security number, right? And so depending on how that is stored, whether it's hashed or not, and there's a lot that you can do with that.
For the sort values, do we store it or
Yeah, that's a good question. Like, because if you store the salt value and that gets compromised, then basically the attacker has two pieces, right? Then they have the hash, the salt, and then they could potentially generate a rainbow table just like that, right? Where they basically take the salt, concatenate it with all possible passwords, compute the hash, and then they have the clear text, right? So yeah, I think that needs to be separate potentially.
so I guess that the users on the one of start?
No, it's the company that has the hash password. And so then when the user authenticates, right, enters their username and password, then it gets well, I think, you know, potentially it could get hashed on the client side and then sent over.
That's really like how can we like verify the password in combination with the salt if we don't know what the salt value that pairs with what password. And since we have the password and the salt, you hash them, you get a hash, right? If like when we want to verify the password, we need the salt.
That's right.
Yes.
Yeah, and maybe there's a way to when you log in, right? It reaches out to the server and says, hey, what's the salt for this particular user, and then hashes it that way. But that has other implications in that you could then potentially query the entire database and say, give me all the salts for all the users, which then is a problematic as well.
Passwords often you have to make them stronger nowadays, so that once if you did a rainbow table, saves look like junk, but you'd be like, oh, I don't think I got it, but you actually did. But people are just using good passwords.
That's right, because if you look up here, there's rainbow tables where it's like, hey, just English words, and then alphanumeric or ASCII 32. And then it's only size 1 to 7, 1 to 8, 1 to 10 is the longest here, right? And so you can only generate rainbow tables for short passwords or shortish passwords. If you have, 16 characters, I don't think that's feasible anymore. All right. Okay, so in blockchain, basically, we can now verify the message sender. We still need a way to quickly look up transactions. We can use a hashing function to uniquely identify transactions and allow the ledger system to easily look up in the ledger. So we have a transaction. Bob sends some USD to Alice, $10. Bob signs it, and now there's a hash that gets generated for that transaction. And so that allows then very easy lookup of that transaction based on the hash. And then we also talked about the hashing function used in the mining context, right? So we have block 2 or block 3 here, the last block with a hash of triple D. And so now the miner that wants to generate the next block will need to take the hash triple D into account when it solves essentially the cryptographic puzzle. And what that then allows you to do, of course, is essentially trace back the entire blockchain based on that hash all the way back to the Genesis block. And let's see here whether I can get my mouse back. Where is it? Okay, so let's look at Etherscan. So Etherscan is a block explorer. So think of it as a visual representation of the blockchain. And there is a block explorer for each blockchain. So the one that I'm looking at right now is Etherscan, which is for Ethereum mainnet. And it allows you to kind of visually explore the blockchain. And so it contains a whole bunch of hyperlinks that allows you to jump into, let's say, hey, I have a block and I want to get all the transactions that are in the block. I want to go to the account. So for instance, here, let me just kind of explain this briefly. So here we have block, this number here, that was generated 31 days ago. It contained 219 transactions. And so now I can click onto these on that link, and now I see all the transactions that were part of this block. Every transaction has a transaction hash, which is the first column here. And then if I click on that, I now see the details of the transaction. I see it's in the block that we looked at first. And it was from this account to this contract. And there were a bunch of tokens that were transferred. So this is a tool that I use daily to understand what is happening on the blockchain. You will become very familiar with this tool as well. But let's go back to the block because I didn't want to show you the entire block explorer. So we have this block right here. And let's see what information we can get out of it. So here we have the hash of the block. And let me make this a little bigger so you see. So we got this block right here, and it itself has a hash, right? So think of all the transactions that are contained in the block, as well as the state of the chain right now. You hash that. That's the block hash. And then there is a parent hash, which essentially, so if we're looking at this block right here, it is essentially is the hash of the previous block. So let's click on that. So it gives you the block. And so if you see here the number, it's 15,467,356, and the block that we just looked at was 57. Right, so you kind of see it's kind of sequence numbers here. It's not guaranteed that they're sequence numbers, but now you can see that 57 ties back to 56 through the parent hash that it contained. And then it itself has a parent hash. And so you can play this game forever, right? So there's 55, maybe 54, etc. So you can go all the way back to the first block that was ever mined, which of course was block 1.